So, chain rule is the next rule that we're going to learn. It's what happens when you have one function inside of another function. So right now, if you had to figure out the derivative of this, you might see that there's a power of 3, and you might be like, oh, I'd like to bring that 3 out in front and subtract 1 from the exponent, and just write it as 3 times 3x plus 2 to the 2. But if you did the definition of the derivative, you find out, oh, it's something else. So right now, all we could basically do with this one is multiply it out. So I'm going to multiply the first 2 together. That'll give me 9x squared plus 12x plus 4 times by another 3x plus 2. And if I multiply that all out, I'm going to get 27x cubed. 18x squared plus 36x squared will be 54x squared. 24x plus 12x will give me 36x. And 4 times 2 will be plus 8. So now I've changed this into a form that we could do the derivative of. Oh, I have an extra one right here. So now if we did the derivative of this, we could take 1 down in front. And we get 81x squared plus 108x plus 36. We might be able to say, hey, I could factor this. There's a 9 in common. That'll leave me with 9x squared plus 12x plus 4. And then factored even further, this factors nicely to be 3x plus 2 squared. And so when we look at the original function, right, remember how I said, wouldn't it be tempting if we could just bring the 3 out in front and subtract 1 from the exponent? Look how close our answer is. But there's a 9 in front. There's an extra multiplication by 3 in order for this one to happen. And you go, oh, that's kind of interesting. So what you end up doing, you say, well, what happens if I did this over and over and over again? And I'm not going to take 3x squared minus 7, by the way, to the power of 40 and multiply it out for you guys. I know that that would be very enthralling to sit through the 45 minutes that that would take, but we're not going to do that. But I'm going to say, let's pretend we did, and then once we got those huge things, let's pretend we had the patience to factor them, and let's look at the results. So if you had 2x plus 3 to the 5, well, it appears that the 5 could come out in front, subtract 1 from the exponent, but then we have an extra 2 that would have to get added. And for this one, it seems to work out like the power rule, but then we need an extra 6x at the end. So when we're looking at that, we're trying to say, is there a pattern? Is there a way to explain things? It seems like so far I've already given away the one pattern, that the power rule seems to be there, right? The number can come out in front and you can subtract 1 from the exponents. But how do we figure out what number we multiply by in the end? Yes? It's just the derivative of the inside function. So my inside function here is 2x plus 3. My inside function here was 3x squared minus 7. Inside function is x to the 4 minus x. Inside function is x to the 5 plus 2. can you see that the derivative of the inside function is what's been highlighted in the green? So to summarize this, if we have one function inside of another function, we do the derivative of the outside function first. And what I mean by that is here, 2x plus 3 is the inside function. The outside function is the power of 5. So if we do the derivative of the outside function first, well, that just means bring the 5 out in front, subtract 1 from the exponent. So when I talk about doing the derivative of the outside function, you keep the inside the same. It doesn't change. And then after you've done the derivative of the outside function, you multiply by the derivative of the inside function. So how do we write that in a general way? Well, in Leibniz notation, this first one here is your derivative of your outside function. And this is the derivative of your inside function. And that becomes your chain rule. I think this notation is even easier to see it. Okay? So g of x here, that's my inside function. F of x is my outside function, f with a little f. And that g of x is inside of f of x. So how do we find the derivative? We do the derivative of the outside function. And when we do the derivative of the outside function, we keep the inside the same. So we do the derivative of the outside function. That might be your power rule, which means you just bring the number out in front and subtract 1 from the exponent. And whatever was inside your function, it stays the same. So that's what I have here with the green. Keep that inside the same. And then after, you multiply by the derivative of the inside function. And so we can do this, and we can even extend this to be beyond. Sometimes we're going to get a function inside of a function inside of another function. So you have like multiple chain rules happening. So I'm going to show you a complicated notation way of doing it that I hope after this time you go, okay, but I'm never going to use that, and that's good. But we're going to start off with an explanation of Leibniz notation and where things come from and how it works. And it has some substitution, and there's some value to it. We'll look at some substitution techniques a little bit later, 2 units from now. But for right now, you're going to find that just this concept that we're going to have, where we do derivative of the outside, keep the inside the same, multiply by the derivative of the inside, is going to be easy enough for us to do. But as far as notation goes, what this is saying is you look at this and you say, what's my inside function? My inside function is 3x plus 6. So you can make u equal to 3x plus 6. So that's my inside function. And then, what does your whole function become? If I replace the 3x plus 6 with u, then my equation becomes y equals u to the 5. Then using the definition of the chain rule with Leibniz notation, it says find the derivative with respect of y with respects to u. dy du says use your variable, y is your equation, so you're using this equation in blue. How would I do the derivative of that? Bring the 5 out in front, subtract 1 from the exponent. Be 5u to the 4. Du dx says, do we have an equation that's u equals in terms of x? Yes, we do, in green. If I took the derivative du dx, what's the derivative of this? It's just equal to 3. Then according to our formula, dy dx is equal to du dx, which we figured out in blue, multiplied by du dx, which we figured out in green. And so our answer becomes 5u to the 4 times by 3, or 15u to the 4. If you then resubstituted back, well, 5 times 3, that's going to be 15. Instead of u, I could write 3x plus 6 to the power of 4 instead of u to the power of 4. Why don't I like this? Well, you have to do a whole bunch of substitutions. It takes a lot more time. If you forget the formula or something along the way, it gets confusing. And it gets even more confusing when we eventually have a chain rule inside of a chain rule inside of a chain rule. So how are we going to do this? We're just going to do it directly. We're going to get good at recognizing what my inside function is and what my outside function is. We're going to get good at looking at this and say, I see that 3x plus 6 is inside of something to the power of 5. So if I'm looking from the outside in, and I sort of think of hugging my function, because you should hug math as much as you can. Anyways, coming from the outside, so from both sides, the first thing I'm going to hit is that power of 5. So if that's my first thing, that's what I'm going to do. I'm going to bring that 5 out in front, keep the inside the same, and now I've done the derivative of the outside function. Then I have to multiply by the derivative of my inside function, while the derivative of 3x plus 6 is just 3, and boom, you get your answer right away without a bunch of extra substitutions that you won't need. So that's how we're going to do the chain rule. But if you want to look at a formula and a substitution way of doing it, you could do it with this. So you're going to get to some functions where they're going to give you a little bit of options. Like this one, you see dividing, so you'll have an option of the quotient rule. You can also, for this one, rearrange your equation a little bit. By making the exponent a negative 4. Then you don't have the quotient rule anymore. And since 3 is just a constant, it's not an actual function, well, not a function with a variable x, this just becomes a chain rule. So I'll do it this way because this is going to be nicer first. I'll do it with the quotient rule as well, just so that you can, like, if you just said, Well, what happens to me if I saw the quotient rule and I went with that first? Is it wrong? No, but it's going to be a little bit more work. So now hug this function. What's our outside function? What's our inside function? Can you see that the x squared plus x is in the inside? The minus 4 is going to be, that exponent is going to be our outside function. So then for our derivative, we'll do the outside function first, which is your power rule. So that negative 4 is going to come out in front. You're going to subtract 1 on the exponent. Keep the inside the same. Once you've done the derivative of the outside function, multiply by the derivative of the inside function, which will be 2x plus 1. So if you think of moving that power 4 to the top of your function, then the derivative happens really quickly. If you decided to do a quotient rule in this one, our quotient rule says keep the bottom the same. So my bottom was x squared plus x to the power 4. Multiply by the derivative of the top. What's the derivative of 3? 0. Minus, keep the top the same. Multiply by the derivative of the bottom. Well, the bottom is a chain rule. So you have the chain rule inside of your quotient rule. So how do I do the derivative of the bottom? Well, my outside function is the power of 4. So that would come out. Subtract 1 from the exponent. Keep the inside the same. Multiplied by the derivative of the inside. 2x plus 1. All divided by the bottom squared. So it's to the power of 4. If I square that, it'll become to the power of 8. This is the same answer as the top one. Again, for all of these questions, you're going to be looking in the back of your book, and it's going to have it in a simplified form. So then your job is to take whichever method you used and manipulate it to get it to look like the form that's in the back of the book. In this case, I think the first method is nicer. It's less things that you have to do, a smaller formula that you have to work with. You're just dealing with the chain rule, whereas the second one you had the quotient rule and the chain rule. Anytime you have square roots, fifth roots, any kind of radical, take the time to change it to a rational exponent. So one of the things, now that we've had the chain rule, one of the things that you're going to approach any question that is asking for a derivative is you're going to be looking for a chain rule. Do I have any functions inside of other functions? And then getting to be able to say, yes, I can see that the 3x squared plus 7x is inside that power of 1/5. So I do my outside function first. The 1/5 comes in front. Keep the inside the same. Subtract 1 from the exponent. And then multiply by the derivative of the inside. So I'm going to get you to try the next one. So again, I changed the square root to a half, but I brought it to the top of the fraction to make it a power of -1/2, just because then it became really easy for the chain rule. So my outside function is that exponent. That -1/2 came out in front. subtracted 1 from the exponent, kept the inside the same, and then multiplied by the derivative of the inside. So here's one that's already done. I mean, it's not been simplified or anything. But can you see that a chain rule has happened? Can you see that the 6x plus 5 is the derivative of the inside of that function? So that means that our original function would have been (3x squared plus 5x to the power of 5). So now we can start mixing our rules. We can start mixing our product rule and chain rule and quotient rule together. So again, the hardest part about derivatives is looking at your original function and then being able to determine what are all the rules for derivatives that are apparent in that question. So first of all, I'm going to rewrite this one, changing the square root of 7 minus 3x to a power of 1/2. Just because any time that we've had a radical so far, we've done that, so we have power rule instead. Then we look at this equation and try to determine what are all the rules that are present. First of all, because I have an x cubed multiplied by another function, and both of those are functions, we're going to have a product rule. We're going to have a product rule where, you know, when we did our product rule and we highlighted things in yellow and green? So yellow is my first function. Green is my second function. I think I just like coloring with highlighters. So there's our two functions. So we have a product rule here. But then when we look at both of those functions, can you see in the green one that you also have a function inside of a function? But we don't have a function inside of a function with the yellow one, because the yellow one is just a basic power rule. So how do we do our product rule and our chain rule combined? Well, if we start with our product rule says keep one the same, so I'm going to keep my yellow one the same, x cubed, multiply by the derivative of the second one. And when I do the derivative of my green one, it's going to have the chain rule. My outside function is the 1/2. So I bring the 1/2 in front, keep the inside the same, subtract 1 from the exponent, and then multiply by the derivative of the inside, which is -3. Plus, keep my second one the same, multiply by the derivative of my first one. So highlighting again, just to show the highlighting is there so that you can see your product rule. Product rule has one the same, derivative of the second, plus the second the same, derivative of the first. When we did the derivative of our second, well, the derivative of our second, in order to do it, we needed a chain rule to do that one. So we had the chain rule at that point. We did the outside function first, the 1/2 came in front, subtracted 1 from the exponent, and then multiplied by the derivative of the inside. Can you see where if we did the substitution off to the side, we'd get a whole bunch of extra stuff, and then we'd have to plug that in later, it might get a little bit, it would get confusing. So it's nice to be able to do it directly. Okay. Can you see that you probably have a quotient rule? Or if you wanted to bring that 1 minus 8x squared to the minus 3 up to the top, you would have a product rule. So I'm going to do this one as a quotient rule. Okay, I'm going to first rewrite it so that my 5x is to the power of 1/2. So I have my function on the top, I have my function on the bottom. Again, since we color-coded these before, I'm going to color-code my top function in yellow, my bottom function in green, just to help us remember the quotient rule. So how does the quotient rule work? Keep the bottom one the same. So here's my bottom one, 1 minus 8x squared to the power of 3, multiplied by the derivative of the top one. So when looking at my yellow one, do I have a function inside of a function? And when you're looking for a function inside of a function, you're basically saying, if I look at my inside function, which is 5x, if I take the derivative of that, do I get something different than 1? Because if I get something different than 1, yes, I have the chain rule. The derivative of 5x is 5. So I do have a chain rule. So my outside function is the half. That half comes out in front. Keep the inside the same. Subtract 1 from the exponent, and then multiply by the derivative of the inside, which is 5. It's a quotient rule, so we subtract. Now we keep the top the same and multiply by the derivative of the bottom, which is our green function. Again, we have a function inside of a function. If we hug that bottom function, the outside function is the power of 3. So we would do that first, bring the 3 out in front, keep the inside the same, subtract 1 from the exponent, and then multiply by the derivative of the inside, which will be negative 16x. All over the bottom squared. So if I have something cubed and I squared, it'll become to the power of 6. And this is where the algebraic fun of your textbook comes into play. They will not write the answer like that. They will simplify that. Okay, so you will learn some simplification tricks. Probably the best simplification trick that you're going to learn in these ones is to realize, okay, first I'm going to color code. First I'm going to color code to show you that this is, oh, that's green. This was your top function where it stayed the same. This is your bottom function where it stayed the same, and your bottom function stayed the same a little bit here. It got squared. That's how your quotient rule works. Bottom function stays the same, derivative of the top minus top function stays the same, derivative of the bottom over the bottom function staying the same and then getting squared. On the top, can you see that there's 2 terms? They're big terms, but in mathematics, terms are separated by adding and subtracting, not by multiplication. So the fact that, I know there's subtracting inside of this here, but this green thing is one thing multiplied by another thing, multiplied by another thing. And this all is multiplied together, making it one big messy thing. Then we subtract. So right here, we're subtracting. That's separating it to another term. And then that second term has 3 things multiplied together. Maybe even 4 things if you think of the 3 as something separate. So for simplifying this, one of the main things to be able to simplify something that's messy is not to multiply it out. Because multiplying this out is going to be tiresome. Because you'd have to do 1 minus 8x squared cubed. I'm already tired. It's just the first thing. And then that has to get multiplied by all of this. So a much better strategy for simplifying is factoring. Look at your first big ugly term and your second big ugly term. And is there anything in common between them? Can you see that your first one has a 1 minus 8x squared 3 times? But in your second one has a 1 minus 8x squared 2 times. So what's in common between them? They both have it at least twice. So when simplifying this to try to make it look like the back of your textbook, you're going to take out a 1 minus 8x squared, because that's in common with both of those. Anything else in common? No 5x. This is a 5x to the negative a half, and that's a 5x to the half. So you could take that out. Do you want to see what that does? It actually works out quite nicely. What would happen if I took a 5x to the negative a half out? We'll look at what that looks like. Okay? Numbers-wise, this has a half, this has a 5, this has a 3, that has a 16. There's no other things left. But if I factored these two things out, what am I going to be left with in my first term? Can you see that I'll still have a 1 minus 8x squared once, because I took 2 of them out. I'm still going to have a half. I'm no longer going to have a 5x to the negative a half. I'm still going to have a 5. In my second term, if you take a 5x to the negative a half out of a 5x to the half, what are you going to be left with? A 5x. Again, think of yourself this way. If I multiply that by that, I'd have to, this is 5x to the 1. The bases are the same. I'd add the exponents together, leaving me with 5x to the half. Can you see that all of your 1 minus 8x squared squared has been taken out? And so we're also left with just a minus 16x. And the reason they do this in your textbook is they'll now say, hey, this term and this term are the same, so you could cancel this out, leaving you with only 4 of those. Yes? Did I forget about the, yes, I forgot about the 3, thank you. Oh, look at this. Squeeze it. Oh, nicely done. Perfectly executed mistake. No, that's a bad, yeah, that's confusing. It was almost a perfectly executed mistake. So I'm going to have the minus. I just want the 3 in front. There we go. Thank you for noticing that. So this will cancel out with that. Okay? It may be that your final answer in the back of your book will look as follows. You will have a 1 minus 8x squared to the 4 on the bottom, and they might also write a square root of 5x on the bottom. Can you see how that 5x to the negative half could go to the bottom and write as a square root? Okay, these are just a lot of algebraic manipulation skills that are going to happen when you're doing your homework. And getting good at this will put you in the top 5% when you get to university, because these are the things that university professors say our students are lacking algebraic skills coming into university. So this is going to be really good for you to practice. They might also put this 2 on the bottom. In fact, I know that they would. In order to put that 2 on the bottom, they would factor the 2 out, the 1/2 out as well, so that that 2 could go on the bottom. Can you see that that would get rid of this? and make this a 6. I erased a 5? When I erased the 3, I erased a 5, so there would still be a 5 in there. Let's make it really... Oh, the 5 was over here. Well, there we go. 1 half times 5 minus the 3, which I'm now saying, if you took out a half, is a 6. Personally, I think right now I'm doing too much work in one line, especially with the erasing. And I think it's a good way to show that when you try to do too much in one line, you end up making arithmetic mistakes. So take your time when you're trying to simplify these. So we would have this in the end. What would be left? You'd be left with, on the top, a 1 minus 8x squared. The 5 that had disappeared would still be there, minus 6 times 5x times a negative 16x. And now they might have expanded the top completely in combined like terms. So you're going to see that your last part of these questions might still take you a fair bit of time manipulating them. But they're all going to be questions that you'll look at your answers, and that is how you're going to say, can I manipulate my question to look like my answer? However, on a quiz or a test, you'll often be just asked to find the derivative, and you won't have to simplify it. So that's what we're going to do for this one. We're just going to find the derivative and not simplify it. And I'm going to give you guys some time to try it first on your own, and then I'll put up the answer. Often it will help you if you take time to manipulate your original function to the easiest way to do the derivative. In this case, that cube root of 1 over x, I manipulated that until I got it to just be a single power, an x to the negative 1/3. So again, this one had the product rule. Add the color coding here. So we had one function here multiplied by a second function here. So we kept our one function the same, multiplied by the derivative of the second one. Then we kept our second function the same and multiplied by the derivative of the first one. With the yellow one, we have a chain rule. Now, once you get good at these rules, it's a little bit of practice. They're not that hard. But what has, the reason I think sometimes in movies they always have calculus up on the board is because if you don't know calculus, for someone to say, you just went from this step to this step all at once, and they look at the answer, and it's so big and so complicated looking and so long that it must be hard. So you must be really intelligent. Maybe that's the bad thing about this course. It's not that hard with some practice, but you have to get your rules together, but you can make some impressive looking stuff happen. And I'm not saying pull this out at parties, like, hey, can I show you some derivatives? You're not going to make very many friends. Trust me, I know. No, just kidding. But, it does look impressive. Oops. Find the gradient. That's another way of saying find the slope of the tangent. Slope of a tangent should make you think, hey, that's my derivative. My derivative finds the slopes of all tangents. And if I want to find a specific one, say at x equals -4, I'm going to find my derivative and then plug in -4 into my derivative, and I'll find my slope. This question doesn't ask you to find the equation of the tangent line. It just asks you to find the slope of that tangent line. So again, before I do my derivative, I look at my equation. Do I need to change anything? I'll change that square root to a half. So I notice that I have two functions that are getting multiplied together. This makes this a product rule. So I start off with my product rule. I keep the first one the same, multiply by the derivative of the second one, and the second one has a chain rule. My outside function was the 1/2, so I brought the 1/2 in front and subtracted 1 from the exponent. The derivative of my inside function is -2. Then the product rule says keep your second one the same and multiply by the derivative of the first one. Again, to help color code things, I like using yellow first. There it stayed the same. Here's my second function, and here's where my second function stayed the same. And the last question here is like what is going to happen when you do your textbook. When you do your textbook questions, there's the question. It's going to say find the derivative, but the derivative in the back of the book looks like this. So you have to not only do the derivative, but then try to work with your answer to get it to look like this. First of all, did you change the square root to x to the half? And then you have your first function versus your second function. So you're going to have a product rule. And in your second function, you do have a chain rule because the derivative of the inside is a -1. And now the fun begins. How do we take that and manipulate that to what we want it to look like? Well, sometimes you get some hints by looking at the answer key. Like, for example, you see that there's a 2 square root of x on the bottom. So it makes sense to take whatever we have as x to the half and change them back to square roots. Well, what would that do? Well, this x to the half, that becomes square root of x there. I multiplied my 2 and my -1 together, get -2 and 3 minus x. I made this a fraction over 1. And then I have plus, and now this 1/2 is going to be a 2 on the bottom, and x to the -half would be a square root of x on the bottom. So I see in my second fraction, I already have a 2 and a square root of x on the bottom, which is something that I wanted. But I wanted a single fraction with a 2 and a square root of x on the bottom. So you can see in the green there, I got a common denominator. If I multiplied the top and bottom by 2 square root of x, I'm going to have a common denominator between my two fractions, and then I'm going to be able to add them. The other nice thing is square root of x times square root of x gets rid of that square root on the top. So now that I've multiplied it out, I've got it all over 2 square root of x. My job now is to try and get the top to equal what the top looks like in the question. In this next step, okay, is something I mentioned earlier. If you can factor early, it's going to save you time as compared to multiplying it all out. So I noticed that in my first big term, I had a 3 minus x. In my second big term, I had 3 minus x squared. So I have a 3 minus x in common in both of those terms. So I factored that out. What's left if I take a 3 minus x out of the first term? just the minus 2 times the 2x, or a minus 4x. What's left when I take 1, 3 minus x out of my second term? I'm still left with 1, 3 minus x. And now we can simplify the top, and it works out to match perfectly with what we wanted to show. Part 2 of this question said, when is the slope of this tangent horizontal? What do you know about horizontal lines and their slopes? Their slopes are 0. So basically, we're asking, when is this derivative equal to 0? And part of the reason this was really nice to factor is a fraction is equal to 0 only when its numerator is equal to 0. And the fact that I've already got my numerator factored, you should be able to see that when you plug in x equals 3, the top will equal 0. Or if you plug in x equals 3/5, that'll make that second factor equal to 0. And so the tangent will be horizontal at x equals 3 and x equals 3/5.